Year 13, Chapter 10, Integration, Lesson 9, Summary of Integration Techniques. In this lesson, we're going to summarise the range of different integration techniques that we have worked on in the preceding 8 lessons. So we're going to start with integration by substitution, and particularly looking at the cases where we can use inspection to carry out the integral in an efficient manner. So let's have a look at the first example. If we have a function of the format ax plus b to the power n, all multiplied by k. Now, notice anything in yellow is a constant, so k, a and b are constants. The power n can be a negative power or a fractional power, as well as potentially being a positive value, but it can't equal -1. We'll look at the specific case where n equals -1 in just a moment. Now, the integral of this function will be k ax plus b raised to the power of n plus 1, and then the whole thing is divided by this new power of n plus 1. But additionally, we also divide by the derivative of this inner function here, which is, of course, a. Don't forget there will, of course, be a plus c at the end, but we're not so worried about that for the moment. So we raise the power by 1, divide by the new power, and we also divide by the derivative of the inner function. So let's have a look at the specific case where the power equals -1, in which case we have a reciprocal function of this format. Again, k, a and b are all constant, so it's just a generic reciprocal function. So this will integrate to an ln function. So we will have the k in place, ln mod, to make sure that we are only taking ln of a positive value, ax plus b. And then the whole thing will be divided by the derivative of this inner function, which means we have this over a. Let's look at the integral of an exponential function. Now, exponential functions integrate to themselves. Remember, k is just a multiplicative constant, so we have ke to the ax plus b. But we then ensure that we divide by the derivative of this inner function here, so we need to make sure we divide by a. So let's now have a look at the 3 trigonometric functions. Because we know how to integrate sine, cos and sec squared, because we can work backwards, remembering that integration can be considered to be the reverse process of differentiation, we can integrate sine, cos and sec squared of these linear functions, ax plus b in each case. So for the first one, we will get negative k cos ax plus b, because sine integrates to negative cosine. But of course we need to divide by the derivative of this inner function, so divide by a. Now, cos integrates to sine, so that's going to give us k sine ax plus b. But again, we need to divide by the derivative of this linear function here, so we have to divide by a. And we remember that sec squared integrates to give us tan, so in this last example we will get tan of ax plus b, but we divide by the derivative of this inner function, like so. Now, we need to remember that in each of these cases, this only works because these inner functions are linear, and that's why we're allowed to use this process of inspection. Now, if the inner function is not linear, then you may have to look at using the more formal integration by substitution process. So one thing to look out for when you're trying to work out which of the integration techniques to use is to watch out for examples where one part of the integral differentiates to another part of the integral, because these have been set up very nicely for integration by substitution to work well. So these might be examples of the following form. So in one type of example, the function that is part of the denominator has a derivative which is some kind of multiple of the numerator. To give you an example of such an integral, let's suppose we had x over x squared plus 5, which we're integrating. If we let u equal x squared plus 5, we can see that du by dx is equal to 2x, which is a multiple of the function in the numerator. So we know when we perform the integration by substitution, a cancellation will occur and we can carry out the integral very efficiently. Other examples which work very well when using integration by substitution are of this format here, where we have a product of two functions and one part of the integral differentiates to a multiple of the other part of the integral. So here's an example. Let's suppose we had to integrate this here. Now, if we allow u to equal x squared minus 3, then du by dx is equal to 2x, and we can see that this is a multiple of this part of the integral, which means when we rearrange, when we substitute, there will be a cancellation of the x part, and we'll be left with an integral which takes the form of the integral of k, some constant, multiplied by u to the power of a half du. And that, of course, can be worked out with the integration by substitution process, but the key principle here is that this is a very, very easy integral to perform. So always be on the lookout for integrals which are composed of one function divided by another function or a product of functions, and where you can spot that one part of the integral, if differentiated, will differentiate to a multiple of another part of the integral. So I wanted to highlight briefly two similar examples which have to be integrated in two different ways. So have a look at them. The first one is x, the integral of x ln x with respect to x, and the second one is the integral of ln x over x with respect to x. So both very similar, both involve ln of x and x, but one is a product of these two functions and one is a fraction composed of these two functions. Now, one of these can be done by parts and the other can be done by substitution. We can't mix up the processes though, so we need to match the correct integral with the correct process. Can you work it out based on what we were just discussing? Well, if you've worked it out correctly, this one here has to be done by parts, and you would need to set u equal to ln x, because you can differentiate that easily, to give you du by dx equals 1 over x, and you would then have to set dv by dx equal to x, which gives you v equals a half x squared, and then when you apply the integration by parts formula in the second part, you take the product of v and du by dx, which gives you a cancellation as you multiply a half x squared by 1 over x, so you get a much simpler integral. Have a go yourselves. Now, in the second example, we need to do this by substitution. Now, we would let u equal ln x, which then gives you du by dx equals 1 over x. And when you then do the fake rearrangement, you get dx is equal to x du, and you can see by replacing dx with this, you will cause a cancellation with this x in the denominator, and your integral ends up being of the format the integral of u du, which is a very easy integral to perform. Have a go at both of these integrals using the suggested techniques. Now, there are two integrals which I think it is worth memorising how to integrate each of them. Now, one of these is the integral of tan x with respect to x, which actually gives you a result of ln mod sec x plus a constant. Now, how do we get to that result? You need to be able to demonstrate how we integrate tan x to get ln mod sec x, and of course we do this by substitution. We need to remember that tan x can of course be expressed as sine x over cos x, which then allows us to use the substitution u equals cos x. Now, we've done this before in a previous video lesson. Have a go yourselves. Make sure you've memorised the process, you know exactly how to do it, you're comfortable and familiar with it, and I think it actually is very useful to memorise the actual outcome as well. So you have that as a solid fact. Now, the other integral that I think it's very useful to know the outcome and the process for getting there is the integral of ln of x. Now, we do this, of course, by rewriting this as 1 multiplied by ln of x. And then, of course, we do this by parts. So we set up u equal to ln of x, so du by dx equals 1 over x, and we set up dv by dx equal to 1, which gives us v equals x. And we can then run the integration by parts process. Have a go yourself. I think it's worth memorising that the result is this. The integral of ln of x is equal to x ln x minus x, and of course plus a constant. It's worthwhile memorising this as well as understanding and being able to reproduce the process that allows you to get from here to here. And again, we've covered this in a previous video lesson, so do go back and revisit this if you've forgotten how to do it. So one key question that we have to address is, if we're using integration by parts, how do we choose each part of the integral? So remember, we would be looking for some kind of product, and within that, one part of the function, which is u, is allowed to stay the same here, and then it's differentiated for the other part of the integral. The other part, dv by dx, is integrated here and here as v. So how do we choose, when we're integrating some kind of product, which part of the product gets differentiated and which part of the product gets integrated? Ideally, our aim is to make this part of the integral simpler than the original integral. So usually, for the part dv by dx, which gets integrated to create v, we usually choose exponentials, sine functions, cosine functions, etc. So quite often, dv by dx will equal e to the x, or dv by dx will equal sine x, or dv by dx will equal cos x in your product. So let's suppose you have an integral which is of the format x e to the x, then of course dv by dx will equal e to the x, same as if you have an integral which is of the format x sine x. Then again, your dv by dx will equal sine x. Now, one key thing if you're looking at using integration by parts and an ln function is involved, this will almost always have to be the u part of the function. It does take practice and it does take experience to become comfortable and familiar with integration by parts, and you usually discover very quickly if you've done it incorrectly, because you will find that this part of the integral over here becomes too complex and you then can't actually integrate the function at all, because as we've said in orange over here, we aim for, when we use integration by parts, the second integral here with the red arrows pointing to it must be less complex than the original integral that you are trying to perform. Otherwise, there's very little point in carrying out the integration by parts. Now, using a trigonometric substitution can be very useful when you are performing certain types of integral. So here are 3 examples. If you have to carry out the integral of sine squared x dx, you need to make sure you are using the identity cos 2x is equivalent to 1 minus 2 sine squared x. If you are carrying out the integral cos squared x with respect to x, you need to make sure you are using a different identity for cos 2x. The identity cos 2x is equivalent to 2 cos squared x minus 1. And if you are carrying out the identity of tan squared x, then use the identity 1 plus tan squared x is equivalent to sec squared x. Now, why is that useful? That's useful because we know that sec squared x can be integrated very easily using the concept of inspection and using the fact that integration can be thought of as the reverse of differentiation. The integral of sec squared x is tan x. So what we need to do is obviously convert the tan squared x integral into an integral of sec squared x, which can be done more easily. Don't forget that some integrals have to be carried out using partial fractions first and then using integration by substitution or inspection. So we're going to have a look at 3 different examples here. Now, the first example is the integral of x plus 2 over x squared plus 4x plus 7 with respect to x. The second integral is the integral of x plus 2 over x squared plus 7x plus 12 with respect to x. And the third example is the integral of x plus 2 over x squared plus 4x plus 3 with respect to x. Now, the first integral, look at the denominator. It does not factorise. Now, that's a good sign that partial fractions isn't going to work here. But what is much more interesting is look at the denominator, x squared plus 4x plus 7, and notice that if you differentiate it, it becomes 2x plus 4, which is of course a multiple of the numerator. So this means we can do this integral by substitution. It's an integral which is of the format f dash x over f of x. So one part of the integral differentiates to a multiple of another part of the integral. Now, look at the second example. Look at the denominator. If you set u equal to x squared plus 7x plus 12, you get du by dx is equal to 2x plus 7, which is not a multiple of the numerator. So substitution won't work. for this one. But what we can see is that the denominator factorises to x plus 3, x plus 4, which implies that we can use partial fractions and then just integrate by inspection or by substitution once you have your simple reciprocal functions. Now, the third example is very interesting because it could be done by substitution. Notice we can say u equals x squared plus 4x plus 3. So du by dx then equals 2x plus 4, which is, again, a multiple of the numerator. So that integral has the format of f dash x over f of x. However, we could also carry out this integral by first using partial fractions. And we can see that the denominator factorises. So it's always worth checking, does your denominator factorise? And does your denominator differentiate to a multiple of the numerator? Now, it's actually integration by substitution that would be much quicker as an integration process, because if you apply the partial fractions, you've then got to run that process and then do the integration afterwards. So if you can integrate by substitution or by inspection, do that first of all. It's a much more efficient process. But it is interesting that there are some examples which lend themselves to two different approaches. There are some integrals which could be carried out by substitution or by parts, and if that's the case, it doesn't matter which method you use as long as you get to the correct answer in the end as efficiently as possible. Usually substitution will be quicker. Now we're going to finish by looking at three similar examples, all of which look remarkably similar but might be integrated in slightly different ways. Here's the first one, the integral of x squared over x squared minus 1. Here's the second one, the integral of x over x squared minus 1. And here's the third one, the integral of 1 over x squared minus 1. Now, which processes do you think would be used to approach each integral? Have a think. The middle one can be done by substitution. Think about setting u equal to x squared minus 1, then du by dx is equal to 2x, which is a multiple of the numerator. So this integral takes the format of f dash x over f of x. It can also be done using partial fractions. Because, of course, the denominator factorises very easily as x plus 1, x minus 1. It's a difference of two squares, but it will be much more efficient to use integration by substitution. In both the other examples, we have to take a slightly different approach. In this example here, 1 over x squared minus 1, we have to rewrite that as 1 over x plus 1, x minus 1, and then we need to use partial fractions first. This will then allow us to break down the integral into two separate integrals, and then we can use inspection or substitution to perform each simple separate integral. Now, the first example is very interesting because we have to do something before we can take this any further. So, x squared over x squared minus 1 is what we might call an improper algebraic fraction. Now, we then either have to perform a polynomial division or use a clever technique to rewrite it before we can perform the integral. So here's what I'm going to do. I'm going to rewrite the numerator as x squared minus 1 plus 1. And we can all agree that that's the same as x squared because the minus 1 and the plus 1 would simply cancel out. And the denominator I leave alone. Now, can you see that here and here, with this and this, we'd get a neat cancellation to give us 1. And then we simply have 1 over x squared minus 1 for the second part. This can then be integrated, first of all, using partial fractions to separate this out, as it's basically become this example over here. And of course, 1 can be integrated on its own to give us x. So 3 interesting examples to think about. So we need to think about which integration process we use and when do we do it. Now, the first thing to always think about is your integral a basic integral, the kind of integral you could have carried out in year 12 before you learnt about any of these integration techniques? It might be in disguise. So to give you an example, I quite often see people taking something like this and trying to use a complex integration process on this. You really don't need to do this. Simply expand the numerator and simplify, divide each term in the numerator by u, and then integrate term by term, as you would using the integration result. The integral of x to the n is equal to x to the n plus 1 over n plus 1 plus a constant. So that is just basic integration. Now, if you've established that something more needs to be used, can you do the integral by inspection? Now, inspection essentially uses the process of integration by substitution, but as we've seen in the previous lesson and also in this summary, if you can do the integral just by almost writing down the answer, then it's a very efficient process. Now, the next question we have to ask ourselves is, does one part of the integral differentiate to be a multiple of another part of the integral? Because if so, then integration by substitution is likely to be the way forward. Now, if your integral is a simple product, you may well be able to use integration by parts if using integration by substitution doesn't look like it's going to work. I would always try integration by substitution first of all, and if that's not going to work, then use integration by parts and see if that works. So you do need for there to be some kind of product present to be able to use integration by parts, and if there isn't an obvious product, then you can always write 1 multiplied by the function like we did in the integration of ln of x, and then try and apply integration by parts. Now, if you find that none of the methods discussed so far work, then have a look at the structure of the integral. If there is a quadratic in the denominator and it factorises, you may well be able to then use partial fractions to break down the integral into separate integrals, and on which you can use inspection or integration by substitution. If the integral involves a sine squared or a cos squared, or a tan squared, then think about using a trigonometric identity first of all to simplify the integral to something that you can then perform using inspection or substitution. There are no hard and fast rules which you can memorise in many ways. It's about experience and it's about practice. The more integration you do, the more confident and more accurate you will become at identifying the technique needed to perform a particular integral. And you should make sure you've really practiced lots and lots of mixed exercises, lots of questions which involve different types of integral, which force you to think about the process needed to carry out each separate question.